and today's topic is Newton's law of cooling as well as the electric current in a circuit. Well, we just had a Thanksgiving, uneventful Thanksgiving, but if we take out a turkey or roast beef, ham out of the oven, then this thing is hot and you have to let it rest, and then eventually the temperature will cool down. What you notice is that rate of change in temperature, right, is proportional to, and then there's a negative sign since it's going down. Now, what is it proportional to? And you might think it's the same thing as before. It's proportional to the temperature of the turkey, right? But that's not entirely true. Because if it's a hot day and your kitchen is like 95 degrees has the room temperature, it ain't gonna cool down as much as during the winter and then you have the windows open. You let it sit by the window, then it's gonna cool down so much faster. So the temperature of the turkey is not the only determining factor of the rate of this cooling down. It has to do with the difference of temperature. So S is a surrounding room temperature. How about that? So this is your differential equation. And of course, your initial temperature at 0 originally, let's say it is, I don't know what the temperature of the baking turkey is. Let's say it's 400 degrees or something. Okay, now we'll solve this differential equation. So we separate the variables same way as before, but instead of just your function, you have this, and T sub S is constant. Now we are kind of assuming that this hot turkey is not going to interact with the room temperature and make the room hotter. It's technically true, but we'll say it's negligible. Your kitchen is big enough compared to the size of the turkey. Now, on the other side, we have K dt. So if we integrate this, then we get ln, and we are sure. And then we have kt plus c. And then we have done this before, so this t minus t surrounding is equal to plus or minus e to the negative kt plus c. Okay? Now we replace this thingy with a, so we have t minus t surrounding is a e to the negative kt, where my a is equal to plus or minus e to the c. So far so good. So it's almost same thing other than you have to carry this extra term. But then this is almost same thing as terminal velocity problem now, isn't it? It's amazing that this completely different situation has exactly same differential equation as a terminal velocity. Now we apply initial conditions. So at this initial condition, left-hand side becomes this, and right side, and then minus this, and right-hand side becomes this. And then once you substitute 0, this whole exponential function dies. So substituting back in, so we have t minus ts is equal to to minus ts. It looks complicated, but these are just numbers. E to the negative kt. So far so good. And if you want to send ts to the other side, then you can do so like this. How about that? Now we can check our answer by doing these couple of things. Number one, if you plug in 0 for t, do we get to back? Let's see. If you plug in 0, then this whole thing becomes 1, and this ts cancels that ts, so we get to back. So that's number one. Number two, we take limit of t as a function as it approaches infinity. And we better get the room temperature. This thing better cool down to the room temperature, but it ain't gonna get cooler than room temperature. Let's see. Exponential function, all of this dies because it's exponential decay function, so we have, and that works out as well. Okay, now, similar problem is the electric current problem, except you are not taking E&M physics yet, so you don't know, but it's kind of what it is, right? Okay, so you're gonna have to trust me on this one now. And then usually this is an alternating current that we briefly talked about in the class, but for now, let's say this is a direct current, 60 volt DC, and that's it. And then how does the circuit, the electric current flow happens? Okay, so we have a differential equation here. I is the current in the circuit, and then is equal to, and I'm going to put it on the other side. So E, I'm going to write down the other part first. So we have negative Ri. I is your variable, R is your constant, like this. And then I'm going to divide both sides by L. So we have R over L, I plus E over L. So far so good. Now, before I can separate the variable, I need to tweak this thing just a little bit. And that just a little bit is factoring this thing out. And we have done this before yesterday. So we flip it over and multiply, and then else cancels, so you get E over R. So far so good. Now separate the variables. So we have the I over I minus E over R is equal to negative R over L dt. Good. Integrate. I'm going to continue up here. So ln, and we're sure once again, I minus E over R is equal to negative R over L t plus C. Good. So I minus E over R is equal to plus or minus E to the negative R over L t plus C. And once again, we replace this with nicer constant, capital A, E to the negative R over L t, and my A once again is plus or minus E to the C, A. Now we apply the initial value at, let's say, your initial current is 0, we just flip the switch on, okay? So let's just say this is the initial value, okay? Then left-hand side becomes just E over R, I becomes 0, and then right-hand side becomes A, and then exponential function dies. So what we have is I minus E over R is equal to negative E over R e to the negative R over LT to the other E over R to the other side. So we have E over R and common factor. And once again, this still looks exactly same as terminal velocity jumping out of airplane. And if you graph this, then it's going to look like this. Let's say, I'm going to graph it here, and we have an asymptote right here, which is, let's just check a couple of things. I at 0, if you put 0 here, right, then this thing becomes 1, so 1 minus 1 is 0, so we have that part checked right here. And then we take a limit of I as t approaching infinity, and then this exponential function dies, so we have E over R. So this E over R is your asymptote. And our function will start here, and then approach asymptote as like that. Good, so that's eventually the final. And then tomorrow I'm going to explain why we want to do such a thing in a circuit. Remind me about that. Okay. Okay.